Hey everyone, in this video we're going to kind of finish up our volumes of solids of revolution with the shell method. Alright, so the idea here is basically that we're going to look at what we might do with the previous method, namely the disk method on this problem, and see why it might be advantageous to use something else, which will be the shell method. So this is the region we're dealing with here in blue, and we're revolving it around the y-axis in this case. So when we actually revolve it, it ends up looking something like this, right? It's very cylindrical at the base since, it's consistent just radius here on the vertical line part, and then kind of goes in as you go up. So how would we do this here? So in this case, since we're revolving around the y-axis, we're going to have horizontal cross sections that are circles. And the main issue, right, is that our radius here, I'm going to draw maybe here in red and here in yellow, you're looking at kind of two different functions around the outside, right? So you have the top part, which is curved, and then this bottom part, which is just a vertical line. And so you kind of have a natural switching here happening at y equals 1/2. And the reason for this is, well, we would want a dy integral, right? So we would be looking for solving for x in terms of y. And so when we look at y equals 1 over 1 plus x squared, this isn't something that's super easy to solve for x. You can kind of cross multiply here and get 1 plus x squared is 1 over y when you divide over. So x squared is 1 over y minus 1. And then x is plus or minus the square root of 1 over y minus 1. So the minus would be if we kind of extended this to the left, but we're only dealing with positive x values here, right? Everything is to the right of the x-axis, so we'd be looking at the positive value here. But the main issue is that we just cut things off here at x equals 1. And so, this curve keeps on going forever. Any value of x makes sense here because your denominator is never 0. And so we just simply have to break it up into, well, the integral from 0 to 1/2, where our radius is just 1. So we just have 1 squared dy, and of course our pi, plus then the integral from 1/2 to 1, where our radius is given by the function, which is square root of 1 over y minus 1. And of course that squared dy. And, you can work it out from here, and it's doable. But it's also not the nicest thing in the world. And so we have another way to deal with this that will allow us to do just one integral. So thus far, every time that we have rotated around a vertical axis, we have used horizontal cross sections, right? We've gone perpendicular to the thing that we have rotated around. And so this time we're going to go parallel. So we're going to be doing things that are vertical, corresponding to our vertical axis that we're going around. And we're going to be using cylindrical shells. Okay, so the picture is pretty important here. And the basic idea is we can draw cylinders with greater and greater radii that will encompass this whole solid. So let's start drawing some of these. Okay, so the idea first is you just kind of start at this point here. It's your center. You go out a little bit, have this little width, right? And then you would take a cylinder kind of corresponding to this. So take this vertical line, go out a little bit, and what's that going to look like? Well, you're going out from the center, you have a little radius, and then we have a cylinder that comes down here. Okay? And then next, I'll do it in a different color here. You would go out, a little bit more here. And then this guy is going to wrap around, right? So you just kind of add it a little bit more. It's going to be a little lower, right? And then this guy is going to come around. And we've got this like cylinder outside the cylinder. So you start with just like one tube, then wrap a tube around it. Then we'll go out another one using red, right? Keep going out a little bit more. Okay, goes down here, comes around. And we have another cylinder outside that. And you can just keep going, right? So basically this is what it ends up looking like. So it's like this tiered cake thing made of all cylinders, and right, it's going to cover everything there. eventually. So basically what we need to learn how to do is calculate the volume that a single cylinder is contributing so that we can then add them all up and calculate the overall volume, right? Just like we did with Riemann sums and stuff, okay? So in this case, let's just look at a specific x value and see what we're computing. So our height is given by the function, right? So we just kind of go up to here. We need it to be three-dimensional, a cylinder, so we give it a little width, maybe say of delta x width. And then this guy gets rotated around the y-axis. So what does this look like? It basically looks like this, right? So we just kind of wrap this one cylinder around, and it goes, behind and everything. And so this is what we want to find the volume of. And it's not really easy, I think, to do from 3 dimensions. So I'm just going to kind of like slice it here and then unravel it, right? So basically just cut it and then unravel, and we should get just a rectangle or like a rectangular prism. And so then the question is just going to be, what are the dimensions? Because this should just be length times width times height to find volume, right? And so my width here is just delta x, right? This is the band that I actually get. We said this was delta x. My height, right? That too we know. It's just given by the actual function value at x, right? This was what determined our height. And then the last question is, what is this length? Well, the whole point here is that we start with a radius of x, and then we wrap around in a circle here, right? And so when I unravel it, I'm just getting the circumference. And so what is the circumference of a circle? Well, it's 2 pi r, and here r is just going to be x. Because, well, that's just how we drew this thing. And so this should be 2 pi x, okay? And thus, we know how the volume is calculated. It's just multiply these three things together, right? So it's 2 pi x times f of x times delta x. And so then when you get the integral, right, so this is just the volume of a single one. So this is really like a delta v, because it's just one single thing, just like one single rectangle in a Riemann sum. And so our integral, well, we're going from 0 to 1 because these are the x values that we allow. And then we're going to do 2 pi x times our f of x, which is 1 over 1 plus x squared in this case. And then the delta x, right, becomes our dx in the integral. And then this is easy to calculate because, well, u is just 1 plus x squared. Du is 2x dx, which we already have. And so this is going to be equal to pi times the integral from, well, when x is 0, u is 1. When x is 1, u is 2, of 1 over u du. And so you get pi times the natural log of u from 1 to 2. ln of 1 is 0, and so you're just going to get pi times the natural log of 2 for the volume. So then, in general, what do we have? So if we have bounds of x equals a and x equals b, so last time it was just x equals 0 and x equals 1, and we revolve around a vertical axis, then we just take the bounds a to b. We have our 2 pi. Here's our r for our radius. So that's the circumference, right? That if you think of the unraveled rectangle or rectangular prism, this is our radius. And of course, the radius is computed from the axis of rotation. Okay, so always think of where you are rotating from. So last time was just around the y-axis, and so it was just go from 0 to x. But if we had revolved around x equals -1, we would have had to go one farther. So always think about that with your radius. It's always from the perspective of the axis of rotation. And then, of course, our height is h of x here. So this is our height. And that's usually just going to be given by the function itself. And so this is the general formula. And that leads me to your exercise. So for the first one, I just want you to set up the integral for the volume of the solid obtained by rotating the region bounded by function y equals 1 plus x squared. in the first quadrant, basically between x equals 0 and x equals 2 around the y-axis. And again, not requiring you to solve, just set it up using the shell method. And then the second exercise is, how would you change that setup if you instead revolve around the vertical axis x equals -2? Okay. Thank you for watching.